person. So the population dynamics is more like a genetic base instead of like individual, like a more physics type modeling that people may see. So before I get started, like, I'd like to acknowledge my collaborators for this work because this is the most recent work that I did with two amazing people. Like Lorenzo is now faculty at the University of São Paulo in Barcelona, and Julio is in the UBS at Stanford University. So how this work started is that like we were working on Stanford COVID project last year, and there has been like so many variants of COVID, and one after another, we are thinking that one of the important questions in public health and epidemiology is that which variant is a variant of concern, and like comparing two variants, which variant is more transmissible and has better fitness over the other variant. So kind of like quantifying this relative transmissibility has been one of the important questions in COVID and other epidemiological applications as well. So those multiple different variants they can be either independent if they're in like a completely different environment, but most often times if they're co-evolving within the same environment, or like one variant is evolving from the other variant, then they're sharing the same environmental either ancestry or like the environmental pressures, such as like a pharmaceutical or non-pharmaceutical intervention. So these population dynamics can be dependent and can be correlated. So, however, the current method for inferring such population dependency or inferring this transmission dynamics, relative transmissibility, is lacking flexibility in modeling in a sense that they either assume certain functional form, like exponential growth, and fit those either genetic data or surveillance case count data to those exponential function, and then like kind of aggregate the results as a post-hoc analysis instead of jointly modeling them together. So as I discussed, coming back to this paper, for example, this is one of the most thorough in terms of current method that we found, but like I will come back to this paper later. So in our work, we found in the current literature or current epidemiology, genetic epidemiology, is lacking that jointly estimating the population history and their dependencies over time. So we are leveraging the flexible hierarchical model to model this dependent population and inference. So quick background, the outline. The top is that I will give you the background of the standard coalescent model. So out of all, I think this part may be the most boring to the current audience, so I will spend some amount of time because it's kind of core of our model. And then like a quick background information in terms of population dynamics from genetic data. And then I will go over our method, and then results, the validation and demonstration in both synthetic and real data. And then because I'm starting new, future directions and quick lab advertisement if time permits. Okay, so the background. So we want to infer population dynamics, meaning that when I say population dynamics in this setting, is that time trajectory of the past population size, aka people call it demographic history in population genetics. So from genetic data, we want to infer those time trajectory of population size. And right now, we're focusing only on the time trajectory, but you can incorporate spatial or like other components as well in more complex extended model. So this kind of population size trajectory inference has been really popular in population genetic and the application of population genetic. For example, the reconstruction of the infectious disease dynamics, as well as the investigating within host evolution, and also like outside of the epidemiology, for example, human demographic history, like out of Africa diaspora, or like the Neanderthal expression, like or non-human organisms as well.
I'm sorry,
yes.
I'm a little lost. What's the input and what are you trying to infer?
So input is the genetic data, like a sequences.
Snapshot?
Yes.
At a specific time?
Yes. Specific sample, so I will get to that when we go to actual.
Oh, it's coming.
Yes.
Okay.
So this is like a still background, okay. General overview.
Sorry.
Okay. Yes. So yes. So from the genetic data, which is a sample in infectious disease, we are sampling over time. So for example, like you sample like 10 individuals from like Cornell, like in January, and then 10 like more people in like February. So, and then you sequence those virus genetic sequences, and then those are our input data. You align them, and those genetic data matrix with the timestamp attached to each data, each sequence is our input data for the inference. So from the genetic data, to get to the population dynamics, there are two sources of variation or stochasticity that add variation in our genetic data. The first one is the genealogical or ancestral process, which is the who. In epidemiology, you can think of who infected who, but in more broader kind of reproduction setting, it's like a who gave birth to who. And then the mutation process, as you can see, this genetic code, like ACGT, like A turning to G, or A to T, kind of stochastic, very jump from one state of sequence letter to the nucleotide letter to the another letter. So to model, we first want to look into this genealogical process. To do that, we need this population model, and we will start with the Wright-Fisher model, which is one of the most basic and foundational population model. So it has a bunch of idealized assumptions. So the population generations are not continuous; it's actually discrete time. So one generation, generation one, generation two, and then the population size is not finite and kept at constant in size n. And the reproduction is that any individual can choose their parent in the previous generation uniformly at random. So it is equivalent to any individual have an equal expectation number of offspring in the next generation. So it kind of models a neutrality, meaning that none of the individual has any selective advantage to produce more offspring than your other people in the generation. And then for now, we are ignoring any population structure. And the mutation process is actually independent of this genealogical process, and we're going to talk about the mutation process later. So, and then we were assuming everything's neutral, and if you know recombination, then we're assuming there's no recombination. So forward time dynamics is that one generation from the next, the next generation person will choose their parent uniformly at random, and then you can trace this by following each generation and keeping the population size constant forward in time. However, if you do that, you have to keep track of every lineage, even though they are not surviving in the current time. So you can actually, and we don't get to sample everyone. Let's say if you have 1 million individuals, and we don't get to sample 1 million individuals in the population. So what we have is that we only have a small subset of the population as a sample, and then we can trace their lineage or ancestry backward in time. So time is the present is time 0, and then time increases going backward in time. So if you trace those a red dot lineage, and you will find the common ancestor sometime in the past. So the quantity that we are interested in is that how much generation we have to wait until they are going to merge to the common ancestor, or coalesce, and what's the rate or frequency of such event. So a simple probabilistic model that if you think about just the 2 individuals in the current generation, and there was the probability that these 2 individuals will coalesce or have a same parent in the preceding generation. So those 2 individuals have to just find one parent. That means that its probability is 1/n because we have constant in size and population. And then the probability of them not coalescing or having distinct parents is just a complement of that, so it's a 1 minus 1/n. So we go back in time, and if they want to maintain distinct parents over G generations, meaning that they don't coalesce over G generation, it's just they are independent process at each generation. So you just multiply the first term by G times, so that's where the probability of G comes in. And then the third line, that if they want to actually coalesce at G generation, if that is a product of probability that they don't coalesce over G minus 1 generation, and then they coalesce at the G generation. So this turns out to be the geometric distribution with the success rate 1/n. So the expected time until the coalescence is the n generation. So what if we have more than 2 individuals in the population? So the probability that those k distinct individuals doesn't coalesce in the preceding generation, it's just you can think of it as a birthday problem. So one individual choose their parent with probability 1, if they can choose anyone. And then the second individual has to choose the parent distinct from the first one. So that's where the n minus 1, they have to choose n minus 1 individual out of n. And then the third person has to choose out of n minus 2 individual, and so on. And then the probability of that have distinct or no coalescent event over G generation is just the power of that probability to the G. So if you just extend it and then just collect the 1 over n term, and then just drop all the higher order terms, then the 1 over n term has the k choose 2 combinatorial factor in it. So what Kingman did is that this is his, I'll give more formal definition in the next slide. But the intuition is if you actually rescale time, so now time was like discrete generation, but if you rescale time in the unit of n generation, and if you take the limit of n goes infinity, that gives the continuous time process with the exponential distribution with the repeat choose 2.
Sorry, should it be probability of k plus 1 having distinct ancestors? I'm just comparing with the formula you had before when you had just 2. You then had 1 minus 1 over n. Right? And here the last factor which you have is 1 minus k over n.
Yes, so, sorry, 1 minus k over n and...
Yeah, so this last factor.
Yes.
It seems like it corresponds to k plus 1 of having
okay.
distinct ancestors rather than k.
You mean like a k minus 1, sorry.
Yeah. Yeah.
K minus 1, sorry, this was a typo, sorry.
Okay.
Yes. Hold on. Hold on. Yes, okay, sorry, there's a typo.
Probably doesn't change the asymptotic analysis.
Yes, with the asymptotic it doesn't change, but it should be k minus 1 is a pretty problem, sorry. Yes, thanks for pointing out. Okay. So the formal definition of the Kingman and coalescent is that it's a continuous time Markov chain on with the taking values in the exchange of partitions of this 1 to n integers. So with the initial condition, with the trivial singleton partitions, and then the transition rate is that the transition rate is 1 if and only if that the next state can be constructed by merging 2 blocks from the current state, and then only on transition different from the current state is 0. And then the process stops when everything is merged together as a one block. So the Kingman coalescent is like only the binary coalescent, and there are other coalescent models where they allow the multiple mergers of the multiple blocks and then also simultaneous mergers of the multiple blocks as well. And also, I have to point out that the choice of blocks to be merged doesn't depend on the block size. So that means that any block number, so if everyone has an equal chance of expected number of offspring, then that's why the block size doesn't really matter. So there are like other skewed offspring distribution coalescent model where you have to weigh in the block size when you choose which one to merge. But in Kingman's coalescent, every block is equally likely to be merged without consideration of its block size. So this jump chain gives you the topology of this genealogy, and so that every tree topology is equally likely with the probability 1 over the number of trees, which is the n factorial times n minus 1 factorial over 2 to the n minus 1. And then the branch length of genealogy is defined or determined by this waiting time, which is called the intercoalescent event between transitions. And then if you construct if you like this D as a number of blocks in that state, then it turns out it's another continuous time Markov chain, which is just a pure depth process. The depth rate at k from transition to k minus 1 is k choose 2. And then the jump chain and then the depth process are independent. Okay, so this, we derived this like based on the right feature model, but it turns out it was proven that many other population model has this chemo-coalescent as a linear process. So that's why this chemo-coalescent has been used a lot. But there, I mean, because I'll talk about this because it's inside terminology. So in real biological population, they may not follow this right feature assumption working on an ancestral process. So this effective population size is the kind of theoretical concept where that the population size, as if they are following the right feature model, they give the same rate of loss or gain of genetic diversity. So kind of loosely you can think of genetic diversity, and if you think about it as a scaling factor of the census population, it is equivalent to kind of multiplying the mutation rate about this with the same factor, complement, I mean 1 over that fraction. So in the right feature model, the effective population size is the same, it's exactly the same as the census population, but like in general, like since population doesn't really, it's not this ideal situation, usually this effective population size is smaller than the census population. So far we look at the constant population size only, but this is not very interesting in our application. So if we let them vary over time, then the rate is now conditionally independent. So it's not like completely independent of each other, but they're still conditional independent. And so if you look at just the time of the coalescent, you can think of as the Markov-Pool process. And using the conditional independence, the density of the coalescent time can be decomposed into the product of the conditional density. And using the coalescent rate, now you have to, it's the exponential rate, but now you have to integrate over the time period. And if you look at this, like they have a very similar formula. If you define this vector as lambda, is the same formula as the Coevolving process. So the inferring this the coalescent time is the same problem as the inferring this Coevolving process density. So the density of the genealogy is defined by the topology and the branch length, which is defined by this coalescent times. So this is the density of the coalescent times, and this is the combinatorial factor of the topology, the probability of observing this given topology, which is the uniform distribution over the number of possible topology. So if you insert this here, then the product of the combinatorial factor cancels out, and the formula of density of the genealogy becomes this like nice expression, where this is the combinatorial factor, just expressed in terms of the time. It's a compact defined notation where it just follows the number of ages left at each time point. So given a coalescent tree or genealogy, once you extract the coalescent time, you don't need a topology, but because the coalescent time itself is sufficient statistic for inferring this underlying effective population size. So this is just an example of the statistical one where realization of the simulated coalescent tree given the constant population size, and the branch length was given as like a mean coalescent time given this constant population size. So if you look at if the population is exponentially expanding or increasing population size, you can see that the terminal branch has very long branch length because it has longer time to coalesce if the population size is large, because the rate is inversely proportional to the population size, and also the numerator is the k2. Okay, and then if you have like such a logistic growth, then you have like another. So this is a demonstration of why this coalescent time distribution informs you about the underlying effective population size of the population history. So in the infectious disease application, or like other, let's say the Neanderthal, the ancient DNA application, for example, the samples are not taken at the same time. So you have this longitudinal samples where you have to keep track of when the samples were taken, because that changes how many ages are available to collect at the time interval. And then also you have to keep track of how many samples were taken at the sampling event. So we are conditioning on this sampling time vector as well as the number of samples, vector number of samples taken at the sampling event as well. So it's the same form, but we just keep track of when the samples are added, or the leads are added, or when the leads are subtracted from the coalescent. So this was a genealogical model, and so because everything is mutual, we can superimpose mutation on the top of it. So we just call it as like a sprinkle mutation on the top of this genealogy. So at each branch, you can think of as a mutation process as a bottom point process with some intensity based on the mutation rate. And there are like many models of mutation. For example, infinite model, meaning that you have like an infinitely long genetic sequence. So every site has each mutation is happening at a new site. So new site gets like a multiple mutation. But you can construct like actual finite sequence as well. And so it is actually, it's modeled as the kind of reversible stationary continuous time of chain. So the substitution model is that, so in this nucleotide, we have A, C to T, for like A and G are 2 rings, and C and T are 1 ring. So usually the substitution between the same number of rings are more likely than changing the number of rings. So the blues are more likely than the red. So you can give a rate for each transition, and also the stationary the frequency vector as well. So depending on how you specify this rate and stationary the nucleotide frequency, there's like an array of mutation models. So the simplest one is that all the rates are same. So for example, everything is 1/3, and the only frequency is 1/4. Then you can actually write down an analytical formula of this likelihood. And this is the but like the most complex one is, of course, when you have all the different parameters for all the rate and all the different the frequency. Then there's the most complex model, but then you have to solve, there's an efficient algorithm to solve numerically for this likelihood. So
what were G, M, and Y?
Oh, sorry. G is genealogy and Y is our data, genetic data. So the probability of observing the genetic data given genealogy, this tree, and then given certain mutation model, and we can drop this mutation on the top of it. We can compute what's the observed probability of this observed genetic sequence in our data.
So are you assuming that only one RNA letter changes when a parent gives birth to children?
No, so it depends on where on the branch, like the mutation occurs. For example, if mutation occurs here, then it affects all the descendants of this from extending from this node. So let's say the mutation occurs here, then like everyone gets this red mutation, and then like if along the subtree, if this mutation occurs here, then everyone gets the mutation. So there are like a multiple, and depending on the model, you can get hit by multiple times. So right now we're assuming infinite sites model, which is the simplest one, is that all the mutation is happening at different sites. But you can also model like a back mutation or like a multiple mutation at the same site.
In yellow are on the same page.
Thanks.
Sure. Okay, so we described the generated model of our genetic data. So there's an underlying population dynamics, which is parameterized by this variable effective population size. And then this population dynamic generates our genealogy, and then we can superimpose the mutation model on the top of it to generate our observed genetic data. So if we go backwards, it's like effectively inverse problem. So given our data, we want to infer what's the mutation parameter, and given certain mutation model, then what is the genealogy, and then from the genealogy, what is the population dynamics. So using this formula, you can decompose into this, the different factors. And okay, so the G is genealogy, and is population blue, and E is the population dynamics, and is certain mutation parameter, and then the tau is just the hyperparameter in our setting. So as we saw from the mutation model slide, we can compute given genealogy and mutation model. We can compute the likelihood of the data. And then, so given the effective population size, we can compute the density of genealogy using our coalescent model. So coalescent model is just a one choice prior. We can use like other types of genealogical model. For example, like there's like a 14 kind birth model, and like other than Kingman, there's like other lambda coalescent, for example. Like there are many other priors you can choose for modeling this genealogical process. So in this step, for simplicity, we'll assume that we have a good point estimate. So in reality, you have to integrate out all possible uncertainties in genealogy. But for simplicity, we will assume that we have a good estimate of the genealogy based on certain genealogy inference model, based on some mutation model from data. And then if we know the genealogy, then we want to construct the effective population size. Yes.
Are you assuming something about the rate of sampling compared to, for example, the branch lengths or something? Or are you...
Yes, so the sampling comes first. That's a great question, and it will come later that we will incorporate our model as a preparation sampling. Okay, so finally, I mean, method is like once we have the distribution inference model with the coalescent prior, method is actually pretty simple to explain. So going back to this paper, they compare the 613G versus the 613D, the transmission or fitness, relative fitness. So they fit the exponential growth model and then apply to either genetic data or the surveillance case count data, and then they define the selection coefficient of one variant over the other as just a ratio of the exponential rate, and just maybe one is just the because G is more fit than the other, so it's just the difference. So the problem of this is that, like, from statistical perspective, that it has a restricted parametric model, and B, even though those trajectories are correlated, their modeling is kind of independent, and C, because they're aggregating kind of post-hoc, the estimate kind of post-hoc. So for example, like a mean of a ratio is not the same as the ratio mean, or like the same with the variance or another statistical estimate. So the uncertainty estimate of this ratio gets lost during this aggregation process. So our approach is that we want to estimate this difference in growth rate and dependency between these populations using the flexible hierarchical model. So we have this shared effective population parameter between population A and population B. So now we are using the genealogy as our data because we, from genetic data with the mutation model, we infer the point estimate of the genealogy. So we are treating genealogy as our data to infer effective population size. But if you want to incorporate the uncertainties in genealogical estimation, we can just like integrate out in the genealogy uncertainty and then estimate directly from data, but it is more computationally expensive. So we proposed a few models. So first one is a parametric model where we have just this is still strict, but it's like a step forward of this the other people's method. So we have the constants, time constant. So this one is the kind of correcting the baseline, and this is the similar interpretation as that their fitness, which is a ratio of the exponential growth. So they are the constant over time, but we explicitly model the dependency in the time trajectory of effective population size. So one thing, because we are not assuming any functional form, what we used is for the effective population size, we use the Gaussian Markov field prior. So we discretize time in a regular grid of the end change point, and then we are in a log scale, so each interval we are estimating with data, and then we are using this conditional dependence or conditional dependence, and try to smooth out this borrowing information from the neighbors, and as well as smoothing out this trajectory, as well as achieving the computational efficiency, because that the precision matrix very sparse, which is just tridiagonal matrix, and then in the tau is the hyperparameter where it just changes this how smooth that you want it to be. So the parametric model, we have the time constant, alpha and beta parameter. But then like we have more like flexible model where we have the dependency changes over time. So this gamma is now time varying dependent parameter. So the same as the other construction is the same as the parametric model, where we also, in addition to any, we model this time varying gamma as the Gaussian recombinant tail, like with a separate smoothing parameter. So going back to the sampling question, so in the standard coalescence, the sampling, we are assuming that it's just the, there's some like, it's not really informative about the underlying population dynamics, but in the epidemiological setting, we see that, for example, in influenza in Europe, where there's a lot of temperate seasonality, when the influenza activity is high, then you get more sequences, and when there's not much influenza activity, when it dips, then in the winter, you don't get much sequences of sample. And for example, in Southeast Asia, when the influenza activity persists over a year, the sampling of numbers are pretty much flat over a period. So this dependency between the sampling process and the process that is being modeled is called preferential sampling. So we want to incorporate this into our model. But you can think of the sampling process as the inhomogeneous sampling process with certain rate. And so if you now this general density, we condition on the sampling time as well, and then the sampling density now depends on the effective population size. So if there's no dependency, it doesn't really hurt anything because, for example, those terms is going to disappear during, like, for example, metropolis hasting. But if there's actual dependency between the underlying population dynamics and sampling effort, not accounting for those preference sampling can result in bias and as well. And also you have to specify certain dependency model like any process. So if the dependency model is incorrectly specified, and it can reduce the, it can increase the uncertainty. So what we do is, again, I guess I can see a trend here. Like instead of assuming the specific functional form, this is called adaptive preference sampling. So just like sampling intensity dependencies, again, modeled with the time varying parameter. So, and also we don't assume any functional form. So this like sampling process is now this sampling process, and this time varying dependency of the sampling with the effective population size becomes RF prior. So the issue with this kind of statistical inference is the parameter identifiability, because we are discretizing time. So we have, let's say, if we have 100 time point grid, then we have 100 parameter of any and also alpha and beta. And for the adaptive model, we have 100 any and then 100 gamma per each time interval. So the identifiability you can think of as kind of bijective net between the parameter and your model. So if you have this bijective net, then from given data, you can infer the parameter uniquely. So for example, this is a kind of silly example. Like if you parameterize Poisson as lambda 1 times lambda 2, even though there's only one lambda, this parameterization is not identifiable because any combination of the scaling factor C will give you the same result. So what we prove is that our parametric model and the adaptive model are identifiable. So the idea behind the proof is that there's a theorem that under exponential family, if the expected feature information is non-singular in a convex set containing the parameter, it is identifiable. So that's what we prove. Okay, so finally, the data application. So in a synthetic data, we simulated 6 possibly relevant to epidemiological settings. So y-axis is in a logarithmic scale. So even though it looks like the linear growth, it's actually exponential growth. So the first setting is that the model where two variants goes under the same exponential growth but with a different rate. But when it takes off, they take off at the same time. And then the second case is the one is flat and the other one is exponential growth. For example, if one variant is endemic in a population and the other one is emerging from the endemic variant, then it kind of takes off as exponential growth. That's case 2. And then the third and fourth one is that there's already ongoing epidemic with the one variant, but the other variant, there's some time delay, emerges from population, and then it grows exponentially together with the other variant. And the fifth case is that one is exponentially decreasing and the other one is exponentially increasing. Possibly the case is that if the vaccination is effective only to one variant, but not in the other. And then the fifth one is the null model where two trajectories are the same. So for comparison, we also considered the vanilla model that the way people do, like kind of taking them as independent, and then we kind of constructed equivalent parameter by sampling from the posterior. So we have our parametric model where there's a time constant dependency with the baseline correction alpha, and then the tilting with the beta. And then adaptive model where the dependency is time varying, and then the adaptive model with the preparation sampling, where the preparation sampling is also time varying. So with the performance measure, we consider like 3 different measures. So DI is the value of the I time rate because we discretize the time. So first one is a deviation, which you can think of as the how much uncertainties you have in our estimate. And then the second measure is the average within the probable interval. And you can think of it as a precision measure. And then third one is the confidence interval coverage, meaning that how much proportion of the trajectory fall within the 95 percentile probable interval. So we think that all three, the good CI coverage doesn't necessarily mean the good CI limit, because the good CI coverage can happen with the huge credible interval, because if you have a huge credible interval, like a lot of trajectory falls within the credible interval, so that gives like a high good envelope measure. So we think that these 3 measures are necessary to quantify our performance. Okay. So I mean, I know tables are bad, but like we tried to plot this, but we must like actually better in tables. So this is like average over all 6 scenarios, and for the bias measure, we can see our adaptive model with the preference sampling does the best. And then so with other measures also, in general, our adaptive model with the preference sampling performs the best, and then the adaptive model without preference sampling is the second, and then usually the vanilla independent model does the worst. And we have to note that our simulation is based on the constant sampling rate. So meaning that if you have actually time varying preferential sampling, our adaptive model with the preference sampling will perform even better. Okay, so now go to the actual real data application. So we look at the first of the delta versus non-delta from one data set from South Korea and the other data set from Italy. The choice of countries are not random because I'm from Korea, and then the ranges from Italy, so they reflecting our personal interest. So we just selected the first state of when delta emerges. So you need some like time period when those 2 variants kind of coexist. So we added some window around that when the delta first appeared and ends when they first stop overlapping. So these are the trees like of the delta and non-delta. You can think of it as kind of a mean estimate of the posterior distribution of the trees. And if you remember the coalescent plot with the varying population size, this one looks very more like the exponential growth because it has a lot of fast branching event with the longer terminal branch, so which signifies the exponential growth, and non-delta looks more like a flat population size. So if you actually look at the case count data, then like in the beginning it was pretty flat when the non-delta was kind of more prevalent, and then it starts taking off with the exponential growth when delta variant starts coming in. So with our parametric model, it shows that the data is actually, so alpha is just a baseline correction, so the growth rate is information is in data. So the data is less than 1, indicating the actually non-delta is like less growth slower than delta. And usually we see the same thing in our adaptive referential model. So these heat maps are kind of a standard way of showing the intensity of the coalescent event and the sampling event within the time interval. Because the more coalescent events happening in the time interval, that means that it will have more information from which you're going to infer your effective population size. So usually the trend is that if you see like more than 10 coalescent events, the treatable interval tends to be smaller because you have more information in the time interval to infer. So we see that good within our parametric model, it shows the exponential decrease, meaning that the non-delta is actually decreasing compared to delta. So it was not as interesting, but in the South Korea case, which is equivalent to our simulated model with the two, because one is flat and the other one is exponentially growing. Okay, so the last one is that with the Italy is more interesting because there looks like there are two exponentially growing populations with both delta and non-delta. So if you look at actual case count data, there's like a first wave of the exponential growth, and then the second wave of exponential growth. So with the parametric model, because of this time delay, like with the constant parameters, you cannot really infer this or model this trend very well. So it kind of fakely shows that beta is greater than 1, meaning that delta is actually expanding faster than delta, which is not true. So in our adaptive time-varying model, we capture this trend very well because in the beginning, the non-delta is actually taking off, and then later, the delta is actually more prominent. So in summary, we constructed a flexible Bayesian model for inferring dependent population size, and then the sampling-aware preferential sampling gives more information, and then we proved the identifiability of the model, and we demonstrated with the real data. So the future, so right now the parameter interpretability is a little bit lacking. So there's actually, you can actually fit the epidemiological compartment model like SIR as the underlying population of magnetics, and then using such things like structural coalescence to actually fit the exponential parameter into the data. So this is another future direction. And then this is just a project I just got started. So all these RNA viruses are very great in the sense that it doesn't, so the evolution is, within host evolution is almost non-resistant because the infectious period is very short and then it's transmitted to the other individual. But with TB, there's like actually latent individual where the bacteria is dormant, and also there's like multiple infections, so and also long infectious period. So there's like within host evolution as well as the multiple independent strain affecting the host. So you can model this latency as something called split coalescence. You can color these branches and allowing them, so the green is like dormant and then the black is active, and they can only coalesce when they're active. So this is kind of a subset of structural coalescent model. And also for the within host evolution, you can model with something called meta-population coalescence, where within host there's like a fast within host evolution phase, which is called close scattering phase, and then the between host, you can model with the collection phase. So there's like a separation of time scale of the within host and then the across host. So finally, the quick advertisement. So our lab is doing, so the interest is that we're interested in the problem that can be modeled with the population genetics and evolutionary processes. So in addition to the genetic epidemiology, we are doing the gene drive CRISPR-based gene drive dynamical system modeling, which is like a reaction difference model network, and also some I know like the other ones. You can see like there are like various topics and the various techniques, but all of them can be modeled in the population genetics and evolutionary processes principles. Okay, thank you. Sorry. Yeah.
Okay, so we know that sort of actual case counts are underestimated. Reported case counts are an underestimate of actual case counts. Does any of this provide information about how many cases there might actually be?
Yes. So the last point I mentioned about the fitting the compartment model directly to the Coalescent Framework. So there has been some work, based on like only only few people are asking this, but there's actually an analytical derivation that there's, in the simple case of a spider model, there's actually direct scaling. So if you assume certain transmission rate or a certain parameter, you can transform this effective population size to actual, actual case count data, counts number.
But you have to filter through a model.
Yes. And also there's a model for jointly modeling of those case count data and then genetic data as well. So that will actually give you more information, but at the same time, it's computationally way more expensive. Like usually people do it in particle filter because like there's a lot of dependency between this case count data and then the genetic data. So it's another venue of interest. Yes.
Yeah, that was really cool. I guess I was wondering, well, what's the minimal amount of data you need, and whether you could, like, if the first time you see an infection is when somebody shows up at a clinic, could you estimate how old that infection is from just that contemporary sample?
Yes, so I think I forgot the formula, but there's a theoretical minimum number that you need, like given the underlying population size. I forgot just the formula, but it's not like a huge number. And also, with, for example, like with the, not this Bayesian framework, but there's a called like sequential Monte Carlo model, you only need like, for example, like 2 samples to construct the coalescent process of those 2 samples. So it depends on like how you parameterize and what kind of inference method you use. But in epidemiology, I think usually you need some like genetic diversity to accumulate over time. So we kind of, for delta versus non-delta, we kind of looked at kind of earlier of delta, like maybe 1 month, but we didn't see much signals. We had to wait a little bit longer to see like what more mutation accumulate. So it depends on also the mutation rate of the pathogen as well. Cool. Any more questions?
So you were talking at the very beginning about models or things like human genetics as well. How does the coalescent picture change when you've got 2 parents and sexual reproduction as opposed to sort of single parent just replication?
Yes, that's a great question. So like even though it's a sexual reproduction, if you don't have recombination, you can just scale n to 2n because then you're just getting like literally 1 haplotype from parent and one parent and the other haplotype from your other parents. But if there's a recombination, for example, like this is like 2 chromosomes and you're in mom, but like in sexually reproducing, like then there's a recombination like this, and then this is the portion going to your offspring. So you have to keep track of this recombining the sequence over time. There's a framework called ancestral recombination graph. So it kind of like it's like you can think of a horizontal gene transfer kind of framework as well. So there's like a mixing of this, joining of this short fragments. And also if you take the marginal, then it will give you a tree of individual segments. But the full picture, you have to keep track of where the recombination point is. So that's like a lot more complex. That's why these viruses are great, but like the humans are very complex. But because the humans are like the most desirable, have the most funding, so there are a lot of advances in that area as well.
Maybe one more question.
Yes.
You talked a lot about the model setup, but you didn't say as much about the actual inference procedure. Is this
Yes.
just Markov chain Monte Carlo based, or
No, so I guess like even the interest of time for this audience, I thought that like I need to cover coalescent model a lot more. But like actual inference, like usually it's done with the MCMC procedure, but in this case, just because of the way we constructed with the JMORF and all this the latent model, we actually used the IMLA, so which is like way faster, and then compared to like full MCMC, even with the Gaussian process, JMRF with the inline shows like more very comparable performance in practice.
Other questions? So if no further questions, let's thank Jaehee and